Let me just start. Yeah, now you can see me. Okay, so thank you. Hello, everyone. My name is Thiago, and today I'll present to you some of the research conducted by Professor Ursula and me on gold and silver Bowtie nanoantennas for solar energy harvesting. It's important to note that this theoretical work was developed during my master program in the CEFET-MG postgraduate program here in Brazil. For this presentation, we'll provide the motivation for the study with a brief introduction to some of the current challenges faced on solar energy harvesting with nanoantennas are and the operational advantages. I will then present the simulation results obtained for the antenna's total efficiency and the radiation efficiency, followed by the study's conclusions and then the final remarks. First, it's important to highlight some of the issues with the most common techniques currently used for solar energy harvest. The photovoltaic solar cells. Widely used and increasingly invested in, especially in countries like China, USA, and Australia, photovoltaic technology has low conversion efficiency due to its physical characteristics reaching commercial values of only 25%, with theoretical cells reaching up to 40 or 50% of efficiency. However, it's important to note that even if the efficiency increases with the improvement of manufacturing techniques and the creation of new materials, this process is theoretically limited to around 88%. Additionally, solar panels are highly dependent of weather conditions, meaning they work uh, only on days with high sunlight exposure. Lastly, as shown in the black body radiation graph for the sun, the operational range of this device is typically between 300 and 1100 nanometers, meaning that only 74% of the radiation energy is effectively available for exciting electrons in the semiconductors, and a significant part of energy, especially in the near infrared and the ultraviolet, is, is wasted. With nanoantennas, whose dimensions range from tens to hundreds of nanometers, energy harvest can reach up to 100% efficiency, depending, of course, the rectifier like associated with the device, and is not limited by the conversion process as photovoltaic panels are. In addition, the low dependence of direct sunlight incidence and the possibility of functioning during both day and night make them attractive for large-scale implementation. Regarding the spectrum, unlike the previous case, the operational range is one of the design parameters, making it possible to build nano structures capable of operating in any band of any width. For this work, the 300-1500 nanometers range was chosen as it is the most energetic, containing about 80% of the energy density provided by the sun. Among the various antenna topology options presented here by the dipole, the bow tie, the square spiral, and the fractal nanoantennas, the bow tie was chosen as the best due to its wide band in the visible spectrum protection for high radiation efficiency, degrees of freedom for design, and symmetry, allowing for simplification through symmetry planes in the simulation model. Regarding the choice of material, it's important to note that at this frequency range, materials are invariable dispersive, and even noble metals can have significant losses as shown in the graph for the imaginary part of the electric permittivity, particularly for gold in green and silver for blue. Furthermore, since the nanoantenna should function like a lens directing the electromagnetic field toward its gap rather than an absorbing structure, absorption must be considered. From this, it's clear that for a large part of the range, both gold and silver perform relatively well, making them suitable choices for the conductive parties. For the substrate, in addition to low losses, there is a requirement for certain inertia in relation to polarization, which makes silicon dioxide and silicon nitride good options for the selection. Silicon dioxide was chosen due to its usability and industrial maturity. With the material selected, optimizations of the nanoantennas whose parameters are presented in this image were carried out considering the existence of 200 nanometers ground plane to ensure total wave reflection and possible resonance in the gap. The particle swarm method and FDTD were chosen for the optimization process. The objective function was the total efficiency, which is simply the integral of the solar electromagnetic spectrum widely weighted by the radiation efficiency of the nanoantenna over the desired range. As a result of the optimizations, total efficiencies close to 50% were obtained, which is a good result for such small wavelength. When looking at the radiation efficiency graph with the optimal values, it's notable that this result is largely due to performance being close to 80% in much of the range, with silver performing better at high energies, explaining its slightly superior total efficiency. The notable spikes in the silver curve are due to FDTD discretization, which does not align the cell with the material boundaries. In conclusion, our work demonstrated that although still unexplored, nanoantennas present a valuable alternative for solar energy harvesting, performing well in wavelengths from 300 to 500 nanometers, meaning a wide band even though noble metals behave as expensive materials rather than perfect electroconductors. The achieved performance were close to 50% total efficiency, showing the feasibility of silver and gold for this type of design. The importance of optimization for achieving the best performance in a wide band was highlighted. As a proposal for future work, we suggest comparing single objective and multi-objective algorithms when aiming for a certain degree of matching between nanoantenna and a subsequent rectifier unit. These are the institutions I would like to thank you, Cefet-MG, CNPq, FAPEMIG, e CAPES, and thank you for attention.
Well, thank you very much, Thiago, for the really nice and the concise talk. So now the floor is open for questions. If you have any questions, please unmute yourself or you simply write it on the chat. Well, I can start. I have a small question. Can you comment a little bit on when you said that theoretical efficiency would be like 100%?
Yeah, okay. When we think about the conventional solar panels, the photovoltaic solar cells, the theoretical maximum efficiency can be around 88% because the convention effect when you have the photovoltaic effect. But when we think about the nano antennas, we don't have this limit, this maximum limit. We can convert all the travel wavelength, all the travel wave in electro signal. But the dependence is principally related to the material. The most important problem when we think about convert energy, uh, travel energy in electrical signal.
So in this case, for example, you are pretty much neglecting the radiation that the nano antennas are going to re-emit, right?
Right. Yeah. Of course, we can't reach 100% of efficiency, but uh, theoretical we can't arrive this limit.
Okay, thank you very much. So are there any further questions?
Hi, Thiago.
Hi.
Can I ask, can you
Yeah.
tell us, can you tell me what will be the like nano dimension you are saying? So how much small dimension you are, I mean, pointing out, figuring out? Because nano structures are like sometimes challenging to fabricate.
Yeah.
How they will,
When you think about the nanostructures fabricated nowadays, we can say that 100 nanometers or 5 nanometers is not a big problem, and we can think in row-to-row process. That is a good option to fabricate uh, a periodic structure in this dimension. So I don't think it's a huge problem when we think about the fabrication, the manufacturing process. Did I answer?
Thank you.
Did
Yeah.
Yeah? Okay.
Okay. Yeah. Thank you. Thank you. Thank you, Thiago.
Any further questions?
Yeah, I have a question. Can you explain more about the materials you propose to use for these nano antennas?
Yeah, our proposal was to use gold or silver as material. And
Okay,
what?
You're saying that you need dispersive materials. What kind of dispersive materials?
The spacer.
I mean, gold and it's a metal, so you need what do you need to do with this gold or aurum? A
Yeah, because
dispersive
of
material.
not a special material. We made our simulations considering only the usual materials, the usual metals, and the usual substrates, because when we think about the high frequency, we need to consider that the materials are not perfect electric conductors when we think about the metals. So we need to consider the losses and the polarizability. So we don't make our research considering different materials, new kinds of materials, only the usual ones.
Okay, then why did you mention dispersive materials?
Dispersion means that they they have a loss factor. The dispersion.
Okay, maybe I misunderstood it. Okay. Okay, thank you.
So I'm wondering what exactly will happen to the efficiency of these materials when you say take into account potential oxidation that would occur, uh, in the environment. Is that a risk factor here, or?
Can you repeat the question, please?
So you have materials that maybe my understanding is a little off, but you're going to be using them as solar harvesting antennas, and they could they or the substrate that they're on could potentially oxidize when they're exposed to the elements. So how will this impact the efficiency of the solar harvesting?
Yeah, in the case of gold, I don't think they provide a oxide inside the substrate. But when we think about silver, you need to consider the oxide effect. So I think it's the important question, and this probably will interfere significantly the performance of the nanoantenna. I think so.
Thank you. This is very interesting. I appreciate it.
Yeah, I think the subject is a little different, but you are used to. But I think it's interesting to learn more about.
Well, I think we don't have any time for more questions. Thank you again, Thiago, for a very nice talk.